I'll make this topic very easy. Click the subscribe button below and watch this unique lecture, auto-ionization of substance or self-ionization of substance. Name the ions present in water. When two identical neutral molecules react together to form cation and anion, then we call it self-ionization reaction or auto-ionization reaction. Now consider two water molecules. They are neutral and they are identical. They react together. Finally, they form hydrogen ion and hydroxide ion. Therefore, water undergoes self-ionization reaction. Now, the first water is water 1, and assume the second water is water 2, and consider the following chemical reaction. In this chemical reaction, water 1 takes proton from water 2. Therefore, water 1 is a proton acceptor, but water 2 is a proton donor because it gives proton to water 1 when we consider the forward reaction. Therefore, these two water react together and form hydrogen ion and hydroxide ion. When we consider the backward reaction, hydrogen ion is a proton donor because it gives proton to hydroxide ions. But hydroxide ion is a proton acceptor because it accepts proton from hydrogen ion. The base in reactant becomes an acid in the product. The acid in the reactant becomes base in the product. This reaction, we call it auto-ionization reaction of water. During self-ionization or auto-ionization, one substance is a proton donor, the other substance is a proton acceptor. For any self-ionization, one substance is a proton donor, the other substance is a proton acceptor. Now let me give you different compounds that undergoes self-ionization or auto-ionization. Sulfuric acid, hydrogen fluoride, ammonia, hydrogen cyanide are substances that undergoes self-ionization. Now, amphiprotic species. Can a molecule or an ion be both a proton donor and a proton acceptor? Can one substance be both proton donor and proton acceptor? The answer here is yes. It can be both a proton donor and acceptor, whether it is ion or substance. That means it can act as either an acid or a base. Now consider the following chemical reaction. Ammonia takes proton from water. Therefore, ammonia is a proton acceptor. But water here is a proton donor because it gives proton to ammonia. That's why we say water is a proton donor. When ammonia reacts with water, they form ammonium ion and hydroxide ion. Now come to the second reaction. Water takes proton from an acetic acids. Therefore, water is a proton acceptor in the second reaction. But acetic acid is a proton donor. In these two chemical reactions, water is amphiprotic species because it became both proton donor and proton acceptor. In the first case, water acts as an acid with a base ammonia. In the second case, water reacts as a base with acetic acid. Now let me give you different example of what amphiprotic species. Hydrogen sulfide ions, bisulfate ion, bicarbonate ions, ammonia, water, hydrogen sulfide are examples of amphiprotic species. Equilibrium constant of water, also known as ionic product of water, represented by Kw, is derived from sulfur auto-ionization of water. Now look to water molecule. They are identical and neutral react. Finally, they form hydrogen ion and hydroxide ion. In this chemical reaction, the first water takes proton from the second water. Therefore, the first water is a proton acceptor, but the second water is a proton donor. When we consider the forward reaction and form hydronium ion and hydroxide ion. But when we consider the backward reaction, hydroxide ions takes proton from hydronium ions. Therefore, hydroxide ion is a proton acceptor, but hydronium ion is a proton donor. And hydroxide ion and hydronium ion react together to form two water molecules. Ionization of water is described quantitatively by equilibrium constant. Therefore, Kc equal to the concentration of hydroxide ion times the concentration of OH ion over the concentration of water square. Look, the ionization of water is described quantitatively by equilibrium constant, and Kc equal to the product of two water ions over the concentration of water square. The concentration of the ions formed is very small, extremely small, and the concentration of water remain constant. It doesn't change. Now, let us multiply Kc by concentration of water square. Finally, we have concentration of water square times Kc. The product of two constant is constant. Concentration of water square is constant, Kc is constant. We multiply these two, we'll get constant. That constant, we call it Kw, is the ion product constant for waters, which equal to the concentration of hydronium ion times the concentration of hydroxide ion. At 25 degrees centigrade, the value of Kw is always equal to 1 times 10 to the power of minus 14. It doesn't change it at 25 degrees centigrade. But if the temperature is changed, the Kw value varies with temperature. Now look, Kw equal to the product of hydronium ion concentration times the hydroxide ion concentration, which is equal to 1 times 10 to the power of minus 14 at 25 degrees centigrade. Don't forget, if the temperature is changed, the K value is changed. Let us take the temperature at 37 degrees centigrade, which is the body temperature of human being. So the value of Kw is equal to 2.5 times 10 to the power of minus 14, because the temperature is changed from 25 to 37. Using Kw, we can calculate the concentration of hydronium ion and hydroxide ion. Impure water. These ions are produced equal numbers in a pure water. Let me repeat it. These ions are produced in equal numbers in a pure water. So their concentration are equal. The concentration of hydronium ion is equal to the concentration of OH ion. Therefore, the concentration of hydroxide ion is equal to 1 times 10 to the power of minus 7 molarity in pure water. If you add an acid or a base to water, the hydroxide ion, the concentration of hydroxide ion, the concentration of OH ion will be no longer equal. And in an aqueous solution, no matter it contains, Kw is 1 times 10 to the power of 1 times 10 to the power of minus 14. Thank you.